Hello everyone. In this lesson, we're going to give a brief introduction to differential equations. So a differential equation is an equation that involves the derivatives of a function along with the independent variable. Now, differential equations play a very important role in all fields of science, economics, and business, since they're used to create models of real-world phenomena. In particular, differential equations are very important to the field of physics, since most of the laws in physics are stated using differential equations. For example, if you think of Newton's law of motion, force equals mass times acceleration. Remember, acceleration is the second derivative of the position function of some object. So there you right away have an equation that involves the derivative of a function. Now down here we have a few examples of some simple differential equations. So here we have a first order differential equation. It's called a first order differential equation because it involves the first derivative of your function that you would like to solve for. And then you have the independent variable x over here. Now, of course, you can solve this one very easily just by integrating the right-hand side, and that would give you that the function y of x is equal to x cubed over 3 plus 2x plus an arbitrary constant c. So this one's pretty easy to solve. Now down here we have another example of a first-order differential equation. Notice we have the first derivative of a function y, and then we have the function y itself over here being multiplied against the independent variable plus 1, and all of that is supposed to equal 0. So our goal would be to find out what the function y is that solves this differential equation. And we'll take a look at some examples of how we can do that later on. Here's an example of a second order differential equation. It's called second order because notice we have the second derivative of the function y that we would like to solve for. And then we have the first derivative here multiplied against the independent variable x. And then over here is just the function y. And then over here on the right-hand side of the equation we have another function of the independent variable x. So this is called a second order differential equation. And now down here we have another second order differential equation. The independent variable in this case is t, and the function is x of t. So notice we have x double prime plus 5 times x equals 0. So we might like to solve this for the function x. And we also have over here some initial conditions. This states that x of 0 is supposed to be 0. And the derivative of x when t is equal to 0 is supposed to be 1. These are called initial conditions, and these allow you to solve for the arbitrary constants that occur when you solve this differential equation. Notice that with this differential equation, because we have the second derivative, we would be integrating twice, so we're going to get 2 arbitrary constants, and these initial conditions would allow us to solve for those arbitrary constants uniquely. Now this type of problem is also called an initial value problem because we're stating what the initial values of x and x prime are supposed to equal. Now let's take a look at this example. In this example, we just want to verify that this function is in fact a solution to this differential equation that we have down here. Notice that this is a second order differential equation, and we also have some initial conditions stated here. So we need to verify that this function satisfies the differential equation and then also the 2 initial conditions. So what we have to do is take the first and second derivative, plug everything in, verify that we get 0 back. So if we start out with x and we take its first derivative, and then its second derivative, now what we need to do is plug these in for x double prime, x prime, and x, and verify that we get back 0 when we add and subtract the terms together. So if we look at x double prime, let's see, that's going to be this. And then minus x prime, so we'll get so that's minus x prime, and then minus 6x. And there we go. That is the left-hand side of the equation right here. And we just need to verify that that's equal to 0. So we just need to add up these terms and show that we get 0. So let's see, if we look at the e to the negative 2 terms, we see we've got 4 and 2, that's 6 of them, and they cancel with this negative 6 e to the negative 2t right here. So we see that these cancel. And then the 9e to the 3t, that cancels with the negative 3e to the 3t minus 6e to the 3t, so they all cancel. And we see that, yes, indeed, we do get back 0. So that verifies that this function is a solution to the differential equation. Now we also need to verify that it satisfies the initial conditions. So notice that x of 0, if I put 0 in here for t, I get 1 plus 1, and that of course is 2, so that verifies that one. And if I look at the derivative evaluated at 0, x prime of 0, so if we put 0 in for t up here, we get negative 2 plus 3, and that is equal to 1, so that verifies those two initial conditions. And there you go. So we have verified that that function is a solution to the initial value problem. Now let's take a look at a solution technique called separation of variables that we can use to solve certain types of differential equations. So one of the most basic and easy techniques to solve a differential equation is to use separation of variables. Now, unfortunately, this only works for a small class of differential equations, so it doesn't work for every differential equation, but it's a starting point. So what you want to do with separation of variables is, if you have a function y and an independent variable x, you want to try to take the differential equation and separate it so all of the y's and dy appear on one side of your differential equation, and then your independent variable, all of the x's and the dx, appears on the other side. And then what you can do is integrate each side with respect to y and x, and then that'll give you a solution to your differential equation. So let's take a look at this example and you'll see how this technique works. So in this example, we want to solve this differential equation. So we have the function y times its derivative minus x is equal to 0. So we want to solve this differential equation and find out what is the function y. So to do this, we're going to separate this differential equation so that all of the y's and the dy appears on one side, and the x's and the dx appears on the other side, and then we'll integrate. So down here, you see right there we have our differential equation that we start with. Now let's replace the y prime here with dy dx. And so then we have this equation here. Now if we take the x over to the other side, you see we end up with this. And now what we can do is think of the dx here as being a variable. Even though it really isn't a variable, just think of it as being a variable. Multiply both sides by dx and you end up with this equation. So now you see here we have all the y's and the dy on one side, the x's and the dx on the other side, and we can integrate both sides. So down here we have each side being integrated right here. So the antiderivative of y is y squared over 2. So that appears here. Now we don't need an arbitrary constant because we're going to have an arbitrary constant over on the right hand side. If we did put an arbitrary constant here, we could just add it over to the other side and create another arbitrary constant. So we don't need one on the left hand side here. So the antiderivative of y we just write as y squared over 2 equals the antiderivative of x is x squared over 2, and we do put an arbitrary constant on that side. Okay, and once again, just to clarify here, you notice if I had placed a constant on the left hand side and then we had another constant on the right hand side, I would just take that over to the other side and create a new constant called capital C, which would be C2 minus C1. So we really only need one arbitrary constant when we integrate both sides. And so here is the solution to our differential equation. We can write it like that. Now we can simplify it a little further. Let's take the x squared over 2 over to the other side. So right here we have it on the other side. And we factor out a 1/2. And then we'll just multiply both sides by 2 to create this equation. So y squared minus x squared equals 2c. Now this is just an arbitrary constant. 2 times an arbitrary constant is just another arbitrary constant. Relabel it as just c right there. And here is a nice form for the solution to the differential equation. So all equations of this form, y squared minus x squared equals c, will solve this differential equation up here. Now, you might not be used to a solution being written like that, but let's just verify that this actually is a solution to that differential equation. So we'll do that by taking the derivative of this equation implicitly. So if I were to differentiate both sides with respect to x, notice we would get this. Okay, now the derivative of the left-hand side is, the derivative of this with respect to x is going to be 2y prime minus, and the derivative of this is going to be just 2x. All right, derivative of x squared with respect to x is 2x, and then the right-hand side here is 0. We can divide both sides by 2, and we get y times y prime minus x equals 0. Yeah, so that verifies that this equation, for any arbitrary constant we put there, does in fact solve this differential equation right here. That's what we just verified. Now down here we have the graph of what various solutions to the differential equation would look like. So if we take this equation here, which is our solution, and we put various values in for c and graphed them, this is what they would look like. So if c is positive, then notice if I tried to solve this for y as a function of x, we would get this. Okay, and then if we take the square root of both sides, we would get y of x equals, now we would have plus and minus the square root of c plus x squared. Okay, so Because of this plus or minus, you actually recover two solutions. Now, both of these would be solutions to the original differential equation. If we look at the plus curve, that would generate these up here, these curves up here, and then the negative would generate the curves down here. Now, if the C is negative, then we would generate the curves on the right and left like we have drawn here. For example, if C is -4, say, so suppose that C equals -4, then we would get the equation. Now for this equation, we want the x squared minus 4 to be positive, so we can take the square root of it without involving complex numbers. And so that would mean that x would have to be bigger than or equal to 2 or less than or equal to -2. So what the positive function would generate then would be these curves right here. It would generate this one and this one over here. And then the negative curve would generate this one down here and this one right here. And so that's what's happening for various values of C that you put into your solution up here. That's what curves are being generated. And also, all of these curves that we have here are known as hyperbolas. Let's take a look at another example. Now here we have a differential equation, y prime plus x times y minus x equals 0, and then we have this initial condition. So what we want to do is try to use separation of variables on this. So here we start with our differential equation. Let's write y prime as dy dx so we can separate the dy and the dx's. Now let's take the xy minus x over to the right hand side, and we get this right here, you see. That's with the x factored out, right? So if we take this over to the other side, we get x minus xy, right? And then just factor out the x and you get this, with the dy dx remaining over on the left hand side. Now let's move the dx over here by thinking of multiplying both sides by dx. And at the same time, we will move the 1 minus y over to the left hand side by multiplying both sides by 1 over 1 minus y. And you end up with this equation right here. Okay, you see that? All right, just move the dx over here, x dx, 1 minus y, divide it to the left hand side, dy divided by 1 minus y, and there you go. Now everything is separated. All the y's and dy's are on the left hand side, and the x's and dx are on the right hand side. Now what we have to do is integrate both sides. So down here we are integrating both sides. Now the antiderivative of 1 over 1 minus y, that's negative the natural log of 1 minus of the absolute value of 1 minus y. Now the antiderivative of 1 over 1 minus y is negative the natural log of the absolute value of 1 minus y. Remember, we had a result like this previously. Okay, using a substitution like u equals ax plus b, it's easy to show that the antiderivative of 1 over ax plus b is 1 over a times the natural log of the absolute value ax plus b, like that. Recall that? Okay, so over here the a is -1 and the b is 1. So you see that's why you get 1 over -1 is negative, and then you get the absolute value of ax plus b. In this case it's 1 minus y. Okay. And then the antiderivative of x is x squared over 2, and we put our arbitrary constant into the right-hand side. Okay, we have to include an arbitrary constant on one of the sides, so we put it over here. And there you go. There is the solution to the differential equation right here. Now we didn't use the initial value yet to solve for the c. Now, what we want to do with this equation is solve for y in terms of x, just to clean it up a little bit. You know, it's nicer to write your solution, if possible, as y equals some function of x. It's nice to do that. So we can do that in this case pretty easily. So in this line right here, you'll notice that we just move the negative over to the other side. Just multiply both sides by a -1. So that moves the negative over here with the x squared. Now, we want to get the y out of this ln. So what we'll do is we'll take e of both sides. Okay, remember e to the ln of a is just a, right? So what we'll have then is e to the ln of the absolute value 1 minus y. That's just going to be the absolute value of 1 minus y, and then we will have removed the ln. And we have to do that to the right-hand side as well. So then what we end up with is this equation right here. So you notice we have the absolute value 1 minus y equals e to the negative x squared over 2 plus c. All right, that might be a little hard for you to see, but that right there is a negative x squared over 2 plus c. Now we can take that, let me just write it over here. Now using rules of exponents, we can write this as e to the c times e to the negative x squared over 2. You see, that's using the rule of exponents that x to the a times x to the b is x to the a plus b. It's using that rule. Okay. And then this is just another arbitrary constant that we will call c. Okay. So right there it is. Okay, so we have c e to the negative x squared over 2 on this side, and you'll notice that we got rid of the absolute values. That's because if we have the absolute value 1 minus y equaling c e to the negative x squared over 2, the absolute value here, we can write this as 1 minus y equals plus or minus c e to the negative x squared over 2. But this plus or minus, we can just call that a new constant c, right? So you end up with this equation right here. So we just absorbed the absolute value into the arbitrary constant right there, and now we can solve that for y pretty easily. We can just think of taking the 1 over to the other side and then multiplying by -1, or you can just think of moving the y over to the right-hand side and subtracting c e to the negative x squared over 2 over to the other side. Now you will get 1 minus c e to the negative x squared over 2, but you can absorb the negative in with the c, and you end up with this equation right here. So there you go. We have found that our y is c e to the negative x squared over 2 plus 1. That is the general solution to this differential equation. And you can verify that if you'd like. Take the derivative of this, put it right there, and then take x times this and subtract x, and you'll see that you do indeed get back 0. Okay, now let's incorporate this initial condition right here and solve for that c right there uniquely. Okay, so that's pretty easy. This equation right here tells us that when x is 0, y should be 3. So if we just plug 3 in for y and 0 in for the x, that's just going to give me e to the 0 then, plus 1. Now e to the 0 is 1, so this tells us that 3 equals c plus 1. And so c is equal to 2. And there you go. So then here is our solution to the initial value problem. Y equals 2e to the negative x squared over 2 plus 1. So this satisfies the differential equation right here, and it satisfies the initial condition. Let's take a look at another example. Now here we would like to solve this initial value problem. So we have the differential equation y prime equals x squared times 1 plus y squared. And we have the initial condition y of 0 is supposed to equal 1. So to solve the differential equation first, for this problem we want to try to use separation of variables. So we'll write this as so we just replace the y prime with dy dx to try to separate the dy and the dx's. Now we'll move the dx over to this side, and we'll bring the 1 plus y squared under the dy, and we get this. And there we go. Now you see that the variables are separated. We have the y's and the dy's on the left, x's and the dx on the right. Now we can integrate each side. Now remember, the antiderivative of 1 over 1 plus y squared, that's the arctangent of y. So the left-hand side here becomes, and the antiderivative of the right-hand side is, and there we go. We have the constant of integration on the right-hand side, but we didn't put one on the left-hand side because, once again, that could have just been absorbed into the one on the right-hand side. So this is our solution to the differential equation. The initial condition here will allow us to solve for the c. Now before we do that, if possible, let's try to write y explicitly in terms of x. We can do that pretty easily here because on the left-hand side we have the arctangent, so we'll just take the tangent of both sides, and that'll give us y on the left-hand side. So taking the tangent of both sides, that tells us that. And there we go. So that's a nice form for the solution to this differential equation. Now let's use the initial condition to solve for that c. So for the initial condition here, we put 0 in for x, 1 in for y, and that will allow us to solve for the c. So we get this. And so we just get 1 equals the tangent of c. So c is going to be the arctangent of 1, which of course is pi over 4. So from here we have c equals arctan. And so therefore this is the solution to the initial value problem. And there you go. That's our solution. Now let's do one thing before we end this video. Let's go back to this problem, let's go back to this solution right here, and let's just verify that this is actually a solution to the differential equation right here. Let's just verify that. Looks a little strange. How can the tangent be a solution to this? Well, it works out very nicely. So let's just verify that right here. So if we take the derivative of this, remember derivative of tangent is secant squared. And then we have to use the chain rule, so we have to multiply this by the derivative of the inside, which is going to be x squared. Now let's notice then that the right-hand side of this equation is going to be okay. Now remember, we have a trig identity. This piece right in here, 1 plus tangent squared, that is secant squared. And we have our x squared then, so what we have then is that the right-hand side is equal to x squared. And yes, we do see that the derivative y prime, which is right here, is equal to x squared times 1 plus y squared. You see that? Both sides are the same. So that just verifies that our solution that we found here was indeed a solution to the differential equation up here. And then we solved for the c by using the initial condition, and that gave us the full solution here to the whole initial value problem. And so that concludes this brief video on using separation of variables to solve differential equations.